Hello, my name is Andrew Carratu. I'm a teaching assistant at MathTopia, and today we're going to be looking at the 2023 AIME II problems 1 through 7. This is the 2023 AIME II problem number 1. The numbers of apples growing on each of 6 apple trees form an arithmetic sequence where the greatest number of apples growing on any of the 6 trees is double the least number of apples growing on any of the 6 trees. The total number of apples growing on all 6 trees is 990. Find the greatest number of apples growing on any of the 6 trees. Okay, so we have 6 trees and the numbers of apples on them, which of course have to be integers, positive integers, or non-negative integers, form an arithmetic sequence, right? So we can define an arithmetic sequence where we start at the first term A and we add D each time. So the first tree, which we'll just say the first tree is the one that it names to be the least number of apples growing on any of the 6 trees, right? So that's this right here. The second tree has A plus D apples. The next tree, A plus 2D. And the next tree, A plus 3D. The fifth tree, A plus 4D. And finally, the last and sixth tree, A plus 5D. Okay, so we have these 6 trees, right? So it's saying that the greatest number of apples is double the least number of apples. So A plus 5D is equal to 2 times A, right? Okay, so let's subtract A, and we get 5D is equal to A. So let's substitute in every A for 5D, right? So the first tree, therefore, has 5D apples. Next one has 6D apples, right? 5D plus D, 7D, 8D, 9D, and 10D. This makes sense. We have an arithmetic sequence, increases by D each time. And the ratio between the least and greatest is 1 to 2, which is exactly what the problem is asking for. Okay, so now the second part, the total number of apples on all 6 is 990. How many apples are there in total? Well, 15D, 15D, 15D. So in total, there's a total of 45D apples growing on all 6 trees. And as the problem says, that equals 990. So all we have to do is divide by 45 on both sides, and this gives us that D is equal to 22. We're not done yet, though, because it's not asking specifically for what the difference between each of the trees is, but what the greatest number of apples growing on any of the 6 trees is. So all we have to do is take the greatest number, which we know is 10D, and we substitute in D. So 10 times 22, we know that's 220. That's our answer. Okay. Okay, this is the 2023 AIME II problem number 2. Recall that a palindrome is a number that reads the same forward and backward. Find the greatest integer less than 1000 that is a palindrome, both when written in base 10 and when written in base 8, such as 292 is equal to 444 in base 8. Okay, so note that from this example it gives us, we already know that there's a 3-digit number that works. So the real question is there something higher that works, right? Well, even though we can only access up to 3-digit numbers when we're less than 1000 in base 10, because in base 8, we can access numbers that are actually 1 digit higher, right? So essentially, because numbers in base 8, right? This digit is is the 1's place. This digit is the 8's place. This digit is the 8 squared place, so 64th place. This is the 512's place. So basically, if we have a 3-digit number in base 10 that's greater than or equal to 512, we'll actually have something in this place. Note that though we can't have a number any higher because this number would be in the realm of thousands, and since we're sticking to less than 1,000, that digit would never be filled in. So we're stuck to 4 digits. So the question is there a number, a 3-digit number, large enough that meets the conditions of the problem where we actually get a 4-digit number in base 8? Well, let's find out. What would the numbers in this number have to be? Well, let's think about what this place would have to be. It can't be 2 because then it would be 1024 plus something, and it's less than 1000. So we know that can't be true. And if it's anything greater than 2, it'll be even bigger, so that's not going to work. And of course, if it's 0, then this place goes away and we're left with a 3-digit number, right? So the only way we could have a 4-digit number in base 8 that satisfies the conditions is if this digit was 1. But because it has to be a palindrome, this digit is also 1. So, in total, we have 513, and then we're adding these 2 places. But these 2 places must also be equal. So let's say x and x, right, go into those 2 digits, and then combining those, we get 72x. So our number has to be in this form when we convert it back into base 10. So the question is there a value of x such that that sum is a palindrome? Well, we can try x equals 0 through x equals 7, which is the highest you can have in base 8, the highest digit. And if we try x equals 0, we get 513, which is not a palindrome. If we try x equals 1, though, we get a total of 585, which is a palindrome. So let's see if we can do any better than that. Well, if x equals 2, then we get 657, which is not a palindrome. If we try x equals 3, we get 729, which is still not a palindrome. If we try x equals 4, we get 801, and so on. We can continue this process. This one number would be 873, and this number would be 945. The last number would actually be 1017, but this number is already bigger than 1000 anyway, so even if it was a palindrome, it wouldn't satisfy the conditions of the problem. So none of these are palindromes, and this is our biggest one. Is it the answer, though? The answer is yes, because every number bigger than 585, well, 585 itself has 1111, or yeah, it has 1111 as its decimal representation in base 8. So any number higher than that, between 585 and 999, would also have 4 digits in base 8. But we've just gone through every number that could have worked, because we just started with the assumption that it had 4 digits in base 8. So there are no numbers greater than 585 that can meet the conditions of the problem. So we know 585 is our answer. And we're done. Okay, this is the 2023 AIME II problem number 3. Let triangle ABC be an isosceles triangle with angle A be 90 degrees. There exists a point P inside triangle ABC such that angle PAB is equal to angle PBC is equal to angle PCA, and AP is equal to 10. Find the area of triangle ABC. Okay, so let's draw out this isosceles triangle. Here's A, here's B, here's C. I'll just draw out the diagram. Angle A, 90 degrees. Let's just pick our point P. Doesn't have to be too accurate for this problem. But we should try. That's pretty much good enough. Here's our angle P. And we're given angle PAB is equal to angle PVC is equal to angle PCA. And AP equals 10. So how do we use this to figure out what the area of ABC is? Well, all we need to do to figure out that area is what the side lengths of this isosceles triangle are, right? We know that they're of the form x root 2. Well, let's try doing some angle chasing because that's definitely going to get us places. So this angle is A, which makes this angle 90 minus A. It makes this angle 45 minus A. And this angle also 45 minus A. And together, these three angles we find tell us two important things about these triangles. First, because these two angles are complementary, this angle in the middle, APC, is 90 degrees. Second, this triangle and this triangle are congruent, are similar by angle-angle similarity. And moreover, because of what we've just wrote in about the x and x root 2, these sides here, right, these respective side lengths are in ratio 1 to root 2. So these two triangles, so basically APB, triangle APB, is similar to triangle BPC with a scale factor of 1 over root 2. Right, we could like say that's K or whatever. So starting from 10 here, we can actually use this to determine what some other side lengths are. For example, this side AP in this triangle APB corresponds in BPC to BP. So by scaling it up by a factor of root 2, we get what BP is, 10 root 2. Furthermore, by repeating the same steps, but this time by considering BP as a part of APB and then mapping it to the respective side length of BPC, which in this case is PC, and we end up multiplying it by root 2 again, we end up with 20. And now we use the other part, the right triangle. And if we use our 10 and our 20 and we use the Pythagorean theorem, we actually get the square root of 500. And that's what x equals. And we could simplify this root, right, by taking out some squares, but we don't even need to do that because what we're looking for is the area of ABC. So we just multiply x by itself, x squared, and then put it over 2. That's what our answer is. 500 over 2, which is 250. And we're done. Okay, this is the 2023 AIME II problem number 4. Let x, y, and z be real numbers satisfying the system of equations. Xy plus 4z equals 60. Yz plus 4x equals 60. Zx plus 4y equals 60. Let S be the set of all the possible values of x. Find the sum of the squares of the elements of S. Okay, so this can be a bit daunting to look at. Like, how do you solve the system of equations, right? Normally, you might know about system of equations in two variables, right? Like, for example, 3x plus 2y and maybe 2x plus 3y, and those are given like some different values, right? And you solve for x and y. And the way you do that is by taking one equation and subtracting it from the other to get a more simplified equation, right? And you might like try to scale some of the equations in some way and try to factor something if it's more advanced. So that's what we're actually going to apply here, just a little bit more complicated. So let's take these two equations and let's think about what they have in common. They have a y and a 4, right, as coefficients of what are like a z and an x, right? It's just that the x and the z are swapped, right? We're just swapping the x and z, really. And in both cases, we're getting 60. And this gets us thinking about what the value of z minus x could be, right? Because what we're really doing by swapping x and z is, in this case, we're adding z minus x times y. And in this case, we're adding x minus z times 4. And it's creating a total sum of 0, which seems to imply to us there's some factorization that equals 0, which is something we really want, because then we'll be able to use the zero product rule to determine one of two factors to be 0. And that's actually exactly what we can do just by subtracting these two equations. So if we subtract these two equations, right, xy minus yz plus 4z minus 4x equals 0. And as I just explained, this ends up being x minus z times y. And this ends up being z minus x times 4. But what's more interesting is if we make it times -4, because then we get x minus z, which is the exact same factor here. So these two factors are the same. And now we can factor it using the distributive property as just y minus 4 times x minus z equals 0. Like I said before, this is exactly what we want because this product equals 0. So one of these two is 0. Furthermore, we can repeat this by using these two equations or these two equations because all we're doing is cycling the variables x, y, and z. And if we tried that, we would get something along the lines of z minus 4 times y minus x equals 0. And x minus 4 times z minus y is equal to 0. So there's 8 different ways to pick which one of these we want. Well, let's start with what's simple, right? If we were to pick at least 2 of these equations, the right side, that would imply that x equals y equals z, right? Because x equals z, y equals x, and then by the transitive property, right, y would equal z as well. So all 3 would be equal to each other. And similarly would follow if we chose these 2 or if we chose these 2. So what value satisfies it if x equals y equals z? Let's try plugging in all variables as x. Well, all 3 equations just simplify to x squared plus 4x equals 60. And if we solve this quadratic, we get 2 different solutions, right? We can use the quadratic formula, or we can just factor it. And if we factor it, we just get x plus 10 times x minus 6. So either all 3 are 6, or all 3 are negative 10. So our set S that we're looking for, we know that it contains negative 10 and 6. We don't know what else it contains, but we will right now. So let's look at what the other scenario would be. Well, first off, what if, well, if we have, okay, so if we have at least 2 of these true, that implies what we've just shown, that it has to be one of those 2 solutions. What if we have none of these apply, right? So none of those 3 equals 0. If x and y and z are like none of them are equal to each other. Well, then that would actually imply that this is true, and this is true, which would imply all of them equal 4. And if we plug that into the equation, we don't get a solution. That's not correct. So therefore, that's not a possibility, which means that we have to have exactly one of these 3 holding, right? We can just pick one without loss of generality, really. And we can just, once we get our solution, we can just realize that it's symmetric. It applies to x, y, z, x, z, x, y, etc. Right? So let's just pick this one to be the true one. So we've shown that 0 is impossible. 2 of them holding leads to one of these 2 solutions. And if exactly one of them holds, so neither of these hold, and then these 2 hold, well then, x equals z equals 4. What does y equal? Well, if we plug it back into this equation, let's try plugging it into this one. It doesn't really matter because in any case, we'll end up with the equation 16 plus 4 times y equals 60. And if we simplify things by dividing by 4, we get that y equals 11. So this gives us the solution of 4, 11, 4. And like we said before, this can apply to this solution, x, y, z, or it can apply to any symmetric. So it can apply to x, y, z, making x equal to 4. Or, for example, it could apply to x. It could apply to y, x, z, right? That would make x equal to 11, which means that our set S gets extended to also include 4 and 11. And that's it. That's all the possibilities. So now we just add up all the elements. Except, wait a minute. Reread the problem, saying sums of the squares. It's a bit tricky like that. We add up the squares. We add up, if we add this up carefully, we get a total sum of 273. There we go. Okay, this is the 2023 AIME II problem number 5. Let S be the set of all positive rational numbers R, such that when the two numbers R and 55R are written as fractions in lowest terms, the sum of the numerator and denominator of one fraction is the same as the sum of the numerator and denominator of the other fraction. The sum of all the elements of S can be expressed in the form P over Q, where P and Q are relatively prime positive integers. Find P plus Q. Okay, so instead of looking at this representation, right, we can just, well, actually, we don't need to use P over Q as the original fraction to avoid confusion, I guess. Let's just say it's A over B. Well, this is what our R is. Our 55R would be 55A over B. And of course, in this case, we're assuming A and B are relatively prime. So this is the most simple form. Well, so B has no common factors with A, but B could have common factors with 55. B could either have 5 as a common factor and not 11. It could have 11 as a factor and not 5. It could have 5 as a factor and 11 as a factor, or it could have neither. Let's go through each of these cases. If it had 5 and 11 as a factor, then this would cancel, and then we'd end up with B over 55 in the denominator. So, like, whatever integer B over 55 would be, because we're assuming that it's an integer, basically, we get this fraction. And as the problem says, the sum of the numerator and denominator, right, of this fraction has to be the same as this fraction. But this can't hold, right? These are both positive rational numbers. So A and B are both positive integers, as the problem states. So that means that there has to be a discrepancy between B and B over 55. In other words, A plus B, if we're looking for whether or not it's greater than or less than or equal to B over 55, by simple simplification, we get 54 B over 55, which we know has to be greater than 0, so therefore it fails. Because the original is greater, and we need it to be equal. So 5 and 11 being divisors of B doesn't work. In a very similar scenario, this case, B having neither divisor, also fails because, well, this one is even more obvious, A plus B versus 55A plus B. Those are differ by 54A, which would only be the same sum if A is 0, which would make the fraction 0, and then it would not be positive. So that also fails. So we're left with these two cases, and these are the interesting ones because we get a number on the numerator that's bigger than A and a number in the denominator that's smaller than B. So theoretically, the sums could be equal. So let's look at that. What would this number be in the first case? Well, okay, B is a multiple of 5, so we divide out the 5 and we cancel, and we get 11A over B over 5. 11A over B over 5. And if we did this case, well, B would be a multiple of 11. We divide by 11 in the denominator, and we divide by 11 in the numerator. Okay, so let's look at the first case first. A plus B is equal to 11A plus B over 5. If we simplify things, we get 4B over 5 is equal to 10A, which gives us 4B is equal to 50A, which simplifies to 2B is equal to 25A, which gives us A over B is equal to 2 over 25. And notice that A and B have to be 2 and 25 respectively, because we can't reduce this fraction anymore, right? And A and B have to be integers. So if we were to divide the numerator and denominator of this by something, it would make A and B not integers anymore. And similarly, if we were to multiply these both by integers, then A and B would no longer be relatively prime, which contradicts with our initial assumption that we're letting this be the relatively prime fraction representation of R. So this has to be true. A equals 2 and B equals 25. That's our only number that we can add to our list of elements, right? So we're adding that to our list, 2 over 25. That's a solution. And let's solve the other equation. So a plus b is equal to 5a plus b over 11. We solve this one, we get 10b over 11 on the left side and 4a on the right side. And we would get 10b equals 44a, and when we divide, 5b equals 22a. And dividing again, a over b equals 5 over 22. And once again, using the exact same reasoning, because 5 over 22 is the relatively prime positive integers, right? That 5 and 22 are relatively prime positive integers. So it's the only way to express that fractional value in terms of that way. We know a is 5 and b is 22. So this leads us to the fraction 5 over 22. And these are our only two elements. There's no other cases. So our answer is just the sum of these two elements. Okay, let's be careful with this though, because 22 and 25 have a pretty large least common multiple. So if we multiply these two, we would get 550 in the denominator, done by multiplying this fraction by 22 over 22, and this fraction by 25 over 25. And by adding this together, we get a total sum of 169 over 550. And we can check if this is two relatively prime positive integers. And that means that our answer is 169 plus 550, which is 719. Yep. All right. This is the 2023 AIME II problem number 6. Consider the L-shaped region formed by 3 unit squares joined at their sides, as shown below. 2 points A and B are chosen independently and uniformly at random from inside the region. The probability that the midpoint of AB also lies inside this L-shaped region can be expressed as m over n, where m and n are relatively prime positive integers. Find m plus n. Okay. So, of course, we're going to try to use the strategy of complementary counting here. This is because the odds of A and B having the midpoint within the region is very common, right? It can be like this, they can be like this, they can be like this, but there seems to be a very specific subset of cases where it crosses over like this, right? And actually, we know that the only way that the midpoint of AB can be outside the region is using this concave corner, because in a convex region, right, like for example here, 2 points and the line 2 points being drawn within the polygon would always imply that the line in between them would only consist of points within the polygon. The only way that this doesn't happen is if it's concave, right? Because then we could have like a corner here and it could dip below, right? Which would cause this to have a point that's not in the region. So essentially, this is the only case where it happens like this. So let's think, right? How could the points be positioned, right? We could have A and P in the same square as each other. That happens with a probability of 1 out of 3, right? Because after we choose where A is, it could be in any one of the 3 squares, and then B is randomly chosen somewhere, and it has a 1 out of 3 chance to be in the same square. And notice a square is a convex polygon, right? It's that there's no way to, it's pretty intuitive. There's no way to draw 2 points within a square such that their midpoint is outside of it. It just doesn't work. So that wouldn't work. And also, if A and B were like this, so one is in one of the squares and another is in another square, such that the 2 squares make up a 1 by 2 domino. How many ways can this happen? Out of 9, 4, right? So it has a probability of 4 out of 9. right? It can be like AB, it can be like BA, or it could be like this in the like this way. So AB or BA. So when that happens as well, because this rectangle, right, looking in this rectangle, there's absolutely no way to draw these 2 points in a way that the midpoint is outside of it. So in conclusion, the only way that it could happen is if A and B are specifically in these two squares, in these two opposite diagonal squares, which happens with probability 2 out of 9. Okay, but this is really where it gets complicated. So we figured out the first fraction. We're going to multiply it by the probability now that assuming A and B are in the opposite squares like this, that their midpoint lies outside the L-shaped region. But what is that probability? Well, let's think about this. Instead of imagining the squares like this, right? Let's imagine this square in between them. Right? And we can imagine that, well, how is the midpoint really determined, right? The midpoint will always lie on this mid square. It'll lie somewhere, depending on where this point is and this point is. And in fact, what's very interesting here is that if we were to map point B over to the same position on the square where A was, then the midpoint on this square would be the same as relative to the position of this point, right? So these 2 points, this point position on this square is the same as this point, right? But now what we realize is that, like, therefore, because A and B, for example, A and B can be in any of these 4 quadrants with equal probability, right? And we think about this middle square and we divide it into these 4 quadrants. And we essentially realize that the midpoint has exactly a 1 out of 4 chance to be in each of these regions. Why? Well, because of what we said before, right? We can imagine moving over B here and then just moving A and B around inside this square and then finding the midpoint wherever it is, right? And then seeing where it lies. But of course, this midpoint is symmetric. Like this midpoint, the odds of it being in each of these 4 quadrants is symmetric probability because A and B can be in anywhere they want throughout the square with equal probability. So it's clearly the midpoint's going to lie in each of the quadrants with equal probability. But as we just said, this midpoint here inside this square is the same relative position as what this midpoint is inside this square. So essentially, there's exactly a 1 out of 4 chance of it lying in each of these 4 regions. And this can be understood intuitively, right? Proving it is pretty difficult, but all we need to know is intuitively this makes a lot of sense. And therefore, the probability of it lying outside the L-shaped region is a 1 out of 4. And this gives us final probability of 1 out of 18. And this is a complementary probability, remember? So we have to subtract it from 1 and get our actual probability of 17 over 18. But we're still not done because it's asking for what n plus n is. And that is 35. All right. This is the 2023 AIME II problem number 7. Each vertex of a regular dodecagon is to be colored either red or blue, and thus there are 2 to the 12 possible colorings. Find the number of these colorings with the property that no 4 vertices colored the same color are the 4 vertices of a rectangle. All right, let's try to draw a nice dodecagon. Doesn't actually matter too much. We don't even need to draw what the actual sides are. We don't need to draw the physical sides of it because this is a problem about their vertices. And actually, I'm going to get rid of coloring them red or blue. And I'm just going to imagine giving them each like, a notation, right? We can like make them positive or negative, right? It doesn't really matter. We're just labeling them with one of two labels. And the whole point is we don't want a rectangle that has all four of them to have the same label, right? So let's think about this. What property of a rectangle, what property does a rectangle have, right? Like if we just took a random rectangle out of this dodecagon, what could we always say about it? And how could we use this in this problem? So here's a random rectangle. If this is actually a square, doesn't really matter. But let's think about this. We know that there are two diagonals of a rectangle, right? And moreover, because of all the 90-degree angles in this rectangle, and the fact that this dodecagon lies on a circle, right? We can use Thales' theorem repeatedly. Essentially, we know this intersection of diagonals is the center of the circle. But how does this help us? Well, let's think about rephrasing the problem around these diagonals, right? So how can we imagine, instead of checking for rectangles within a dodecagon that have all vertices the same color, what if we just checked the diagonals, right? So here's a setup, right? Let's just pick an arbitrary setup of points. Doesn't really matter. Just, I'm gonna put a random rectangle in it somewhere, and we're just going to try to come up with an efficient way to find that rectangle. So we're just gonna do that. Okay, so clearly there's this rectangle here of the negatives, but trying to search through all the rectangles is a very strange process and it's hard to define, and that is what makes this problem difficult to determine the number of colorings. But instead, let's just draw the diagonals. All these main diagonals, the diameters of the circumcircle that pass through the center. And now we're going to actually just, for each of the diagonals, we're just going to take both of these points. So for example, that was positive and negative, right? We're going to, we know that we are going to mark this with a 0, right? What about this diagonal? Plus and minus, those cancel. We're going to mark that with a 0. What about this one? Negative, negative. Well, let's mark that with a negative sign. What about this diagonal? Oh, positive, positive. Let's mark that with a positive sign, right? And what we're really just saying is we're labeling it with a 0 if they have different, right? If they have different symbols, and we're labeling them with the symbol that represents both of them if they're the same symbol, right? So negative, negative, we put a negative, positive, positive, we put a positive, positive, negative, we put a 0. It's just a nice, strange way to think about it, but doesn't really matter anyway, how we think about it. Oh, this is interesting. I accidentally put another rectangle into here, right? And essentially, hopefully you can see where we're going with this. And that's the fact that there is a rectangle with all four vertices the same color, if and only if among these 6 symbols that we draw here, we have at least 2 positives or at least 2 negatives. And the answer for this, the reason for this is simple. Because, for example, if we have at least 2 negatives, we take that diagonal, we take the 2 points there, we take the diagonal with 2 negative points there, and we just connect those 4 points together. And because we took these 2 diameters and we connected the points together, this is actually guaranteed to be a rectangle. And this is because we use the reverse of Thales' theorem repeatedly to show this is a right triangle. Like this is a right triangle because its hypotenuse is the diameter of its circumcircle. This is a right triangle, and then this is a right triangle. This is a right triangle, and it's a rectangle. So we always know. We've proven the statement that if we have at least 2 positives or 2 negatives, we get a rectangle, right? And if we have a rectangle with all 4 the same, we know that those two, it has to consist of two diameters, which through our notation system give us two different diagonals with the same symbol. So now all that's left to do is to redefine the entire process of choosing the points to be red or blue around this new diagonal system with the notation and everything. So let's try to do that. Well, in fact, that's not even too hard. So let's erase all of these and let's try to define a process for how we decide what the diagonals, what all the coloring of the vertices are. So we go through and we label every single one either positive, negative, or 0, right? So let's just say we have this set up, right? Now for the positive ones or negative ones, it's automatically guaranteed what the colorings are. But if we have, for example, a 0, we don't know which one it is. So we flip a coin, whatever. We just decide if it's positive and negative or negative positive. And what this is doing is it's allowing us a good way to count, because we now have only 4 cases actually, which is the 0, 0, 0, 0, 0, 0 case, all of them being 0, one of them being positive, one of them being negative, so like maybe this one being negative, or one negative and one positive. Those are our only possibilities. And we can see why, because we have to have either 0 or 1 positives and 0 or 1 negative. So let's go through each of the cases, right? If we have all zeros, right? So let's just like the all zeros case, or we have 1 positive, or we have 1 negative, or we have 1 positive and 1 negative. In the all zeros case, all 6 of them are just chosen to be 0. We have no way to choose it in any other way. All we're doing is we're taking each of the diagonals, all the main diagonals, all the diameters, and we're picking at random which point has red, which point has plus, which point has minus. It doesn't really matter what you call them, plus, minus, red, blue. We're just picking one to be one to be the other. Clearly that's 2 ways to do that, and it's to the power of 6 because we're doing it 6 times for each of the 6 diameters, which gives us a total of 64 possibilities. Now for one positive being among them, then we pick somewhere to be a positive. There's 6 ways to do that, right? We can pick this one to be a positive, or we can pick this one to be a positive, doesn't matter. And then, well, the positive diameter has to have 2 positives, and there's no way to do it except one way. So the probability that we're multiplying by isn't 2 to the 6, but only 2 to the 5. And this is 32 times 6, 192. And using the exact same logic, 6 times 2 to the 5th, right, is 192. And then the final case, plus and minus, we decide some place to choose a plus, some place to choose a minus. That's clearly 6 times 5. And then finally, it's just 2 to the 4, because each of the zeros we have remaining, those all have 2 ways to do it. And that gives us 30 times 16, which is a total of 480. And we just add together these numbers, and this gives us a total of 4, 2, 3, 4, 5, 928. There we go. Yeah, and for more learning about high school and competition mathematics, you can go to mathtopia.com/mt-press.